All right. Welcome back for tuning into some more kinetics question, right? Everything you wanted to know about kinetics, but were afraid to ask. So what we're working towards with kinetics, again, is the study of the rates of the reactions. And ultimately what we want is we want a formula or some way of calculating what would the concentration be versus a function of time. So if I have a chemical reaction and I want to monitor the progress of how many products are being produced as a function of time, or how quickly my reactants are going away as a function of time, right? I have a mathematical way of doing that. And that's what's known as the integrated rate law. So the integrated rate law is a mathematical formula that allows me to calculate concentration as a function of time. So in this case, we're going to look at a certain insecticide and how it decomposes in water at 12 degrees Celsius. And what we know is that that follows first order kinetics. And so we know that if we double the concentration, we double the rate. That's the meaning behind the first order kinetics. We're given a rate constant of 1.45 years to the minus 1. Right, so this reaction proceeds at a rate that we measure in units of years rather than seconds. So on June 1st, some of this insecticide accidentally washed into the lake, and the lake had a concentration of 5 times 10 to the negative 7th grams per centimeter cubed. So not a large concentration, but certainly enough that it might impact the aquatic population. And so we're going to assume that the temperature of the lake is constant, right? There's no variation of temperature, so that isn't going to influence the rate of the reaction. And so what's the concentration of that insecticide on June 1st of the following year? So if we wait 365 days or 366 days, if it happens to be a leap year, but if we wait a full year, what would the concentration of that be, right? So when we look at a first order rate law, right? First order rate law, our integrated rate law is going to be that the log of the concentration of A at time t is equal to minus the rate constant times the time plus the log of the initial concentration, right? So if I take the rate constant, how long it's been, and my initial concentration, I can calculate what's the concentration at time t, right? So I'm looking for what is the concentration, so what is the log of A of t, right, when my rate constant is 1.54 years to the minus 1, so I have minus 1.45 years, times my time, right? Well, my time was 1 year, plus the log of my initial concentration, right? My initial concentration was given as 5.0 times 10 to the negative 7th, right? So that means that my log of my insecticide, right, is equal to minus 1.45 plus the log of 5 times 10 to the negative 7th, which is plus a minus 14.51, which equals a negative 15.96, right? So the log of my insecticide after a year, right, is going to be equal to negative 15.96, right? So if I want to solve for that, right, I got the log of this equals negative 15.96, right? Then we're going to use the inverse natural logarithm, or e to the x, right? So the log, right, or, right, let me rewrite that. And so my concentration of A at time t is going to be equal to the value of e raised to the power of negative 15.96. Right, and so that's going to equal 1.2 times 10 to the negative 7th. That's a 7 grams per centimeter cubed. Okay, so our units have to be the same, right? So we started out with a concentration in grams per centimeter cubed, so we end up with the same concentration of grams per centimeter cubed. All right, so that's going to be the concentration following a full year. Okay. So part B of that question says, well, how long is it going to take for that insecticide concentration to decrease to 3.0 times 10 to the negative 7th grams per centimeter cubed, right? So in this reaction, in this equation, right, in part B, they're giving us A at time t. So they're saying when you have a concentration equal to 3 times 10 to the negative 7th, what's your value of t going to be, right? So this time we're going to set up this reaction and we're going to solve for t, right? So if we take our reaction log of A at time t equals minus kt plus ln of my initial concentration, then I'm going to say the log of 3.0 times 10 to the negative 7th equals minus 1.45 times t plus the log of 5.0 times 10 to the negative 7th. And so I'm going to solve for t. T equals minus ln of 3.0 times 10 to the negative 7th minus ln of 5.0 times 10 to the negative 7th, right? Divided by my k of 1.45, and that equals, I get a negative minus 15.02 plus 14.51, right? Those are my two values there. Divided by 1.45 years, and that's going to equal a total of 0.35 years. All right, so it's going to take about a third of a year for the concentration to decrease to my value of 3 times 10 to the negative 7th. All right, and that's less than, right? That value is greater than what we calculated in part A, right? In part A, we had a concentration of 1.2 times 10 to the negative 7th. And so if it's only been a third of the year, then we should still have more insecticide in the lake after that. Okay? All right. Now we've got a question where we're going to look at and say, okay, what is the reaction order if we're given the integrated rate law? Right, so here we have some data, right? We did an experiment and we want to determine what the rate law is. What is the integrated rate law, right? Well, again, when we look at kinetics, we're looking at rate laws. We can't just look at a balanced chemical equation and figure out what the integrated rate law is, right? Again, we have to get our little chemist hands dirty and figure it out by actually performing the experiments, right? So in this question, right, we've got some data here and we've got time and concentration of NO2. We're looking at the decomposition of NO2, nitrogen dioxide decomposing to form nitrogen monoxide and oxygen gas. Is the reaction first order or second order in NO2, right? And so we're given the concentrations at various times and asked to figure out, is it first order or second order? Right. Well, what we can do, right, is if we look down here at this table, right, we've taken our concentration of NO2 and we've calculated the log of the concentration, and we've also calculated 1 over the concentration, right? So we have the concentration in units of molarity, we have the log of the concentration at all these different times, and we have 1 over the concentration at these different times. So the next step then is to actually plot that data, right? So we want to plot, right, on a graph, right? We're going to have two graphs, right, where we're going to have time on our x-axis, and we're going to have the log of concentration, right, versus time, and we're also going to have time plotted versus 1 over the concentration versus time. We want to look for which graph gives us a straight line, right? If we plotted just concentration versus time, right, and we got a straight line, then that would tell us that's a zero order reaction, right? If the concentration versus the time gives us a straight line, that's a zero order reaction. If I have log of x versus time, right, and I get a straight line, then that's first order. If I have 1 over x versus time, and that gives me a straight line, then that's a second order reaction, right? So we plot the data to see which one of these gives us a straight line. And then from that graphical data, we can determine the order of the reaction, right? So when we plot this data and we're plotting the log of the concentration versus time and 1 over the concentration versus time, right? These are the graphs that we get. Log of concentration versus time kind of has a little bit of a curve to it. Not exactly a straight line, close, but not close enough. But if I look at 1 over the concentration versus time, that gives me a straight line, right? So knowing that 1 over the concentration gives me time, then I know that this is a second order reaction, right? Just simply by looking at the graphical data. Okay? So there you go. All right. Half-lives, and we'll talk about half-lives more when we get into radioactivity, nuclear chemistry, and talking about nuclear decay and those different processes. And so in this one, we're going to look at the half-life of a first-order reaction, right? And half-life just simply means how long does it take for half of it to go away, right? If you start with a pound, how long does it take for you to have half a pound? If you start with a metric ton, how long does it take for you to have a metric ton, right? And so that's what we'll be looking at. And so this is the reaction of C4H9Cl with water. We know it's a first order reaction, right? And then we want to estimate at what point would we have half of it, right? How long is that half-life? Okay. And so if we start off with 0.1 molar of our concentration of our C4H9Cl, right, then half of that would be down here at 0.05 molar, right? And so when I have 0.05 molar, right, that would be the point on the graph where I have a concentration of 0.05 molar, right? Well, how long did that take? Well, that took approximately, right, about 340 seconds, right? And that's just an approximation, right? Just looking at the graph to say that it looks like this reaction has a half-life of 340 seconds. So what you start with, half of it will have reacted in 340 seconds. Part B of this says use the half-life to calculate the rate constant. All right, well, one of the nice reactions, one of the nice equations that we have with half-lives and first-order reactions is that the rate constant is equal to the log of 2 divided by the half-life. Right? And that's written as T1 half, right? So how long does it take for half of it to go away? And it's log of 2 because we're reducing it by a factor of 2. Well, the log of 2 is equal to 0.693. So 0.693 divided by the half-life is going to give us the rate constant. Well, 0.693 has no units, so that's unitless. And my half-life was 340 seconds. So 0.693 divided by 340 seconds, 2.0 times 10 to the negative 3 seconds to the minus 1, right? That's my rate constant for that reaction. Okay, so I figured out by graphical representation the half-life of my first order reaction and then what the rate constant is for that first order reaction. Okay? Let's look at activation energies. Right? So activation energies and speeds of reactions. Okay, I have a series of reactions, right? And we want to look at these three reactions, right? And we want to rank them from the forward rate constants, right? So what's the value of the rate constants moving forward, assuming all three reactions have nearly the same value of the frequency factor, right? And so again, what we look at is that frequency factor that comes from the Arrhenius equation. And in the Arrhenius equation, right, there's that value of A, which is what's known as the frequency factor, which is related to the number of collisions and the number of effective collisions, right? But basically, what we want to take from that, right, is the important thing to look at is that when I have a lower activation energy, right, then that gives me a larger rate constant and I get a faster reaction. So lower activation energy gives me a greater rate constant and a faster reaction. Okay. The change in energy, right? So you're looking at these graphs and seeing, okay, there's a change in energy from reactants to products. That doesn't factor into the value of the rate constant. So I'm just looking at ranking the activation energies, right? So the ones with the highest activation energy is going to have the smallest value of K and be the slowest reaction. So that would be reaction 2. All right, reaction 2 has the highest activation energy, so that's going to be the slowest. The next slowest, or the next fastest, I guess, would be reaction 3, because that has an activation energy of 20 kilojoules per mole, right? From reactants to the top of that graph, that's my activation energy. That's going to be 20 kilojoules. And then the fastest reaction is going to be reaction 1, because that only has an activation energy of 15 kilojoules. Okay. So that's my activation energy ranking. This one's going to be the slowest. This one will be second, and that one will be first. Right, in order of increasing rates of reaction, right? So we can also graphically determine the activation energy of a reaction, right? And so what we can do is we can look at a graph, right? And we've got, this is our reaction of the rearrangement of methyl isonitrile, CH3NC, which rearranges itself into CH3CN, or acetonitrile. And at various temperatures, we've got different rate constants. And so we're asked to calculate the activation energy from that reaction, okay? And so what we want to do is we want to determine what that activation energy is, right? And so we can get activation energy from a slope, right? So if we plot the log of K, right? So if we plot a graph, right, we've got K versus temperature, right? If I plot log of K versus 1 over the temperature, right, I'm going to get a line, should be a straight line, right? And the slope of that line is going to be equal to the activation energy divided by R. R being my gas constant, my universal gas constant, which has units of joules per Kelvin per mole, right? And so when I plot that graph, right, I get a nice straight line that looks like that. So I've got K, right? And then I'm going to look at plotting log of K, right? So I've got K. I would take the log of K, right? And I would calculate those. And then I would calculate 1 over the temperature, right? And I would calculate those. And again, temperature is going to be in Celsius, right? But I need temperature to be in Kelvin, right? So temperature in Celsius when I use my plot, because I'm using R, right? I'm using the gas constant. Remember, gas constant, we always have to be in Kelvin, okay? So if I have log of K versus T, I get a slope, right? And that's going to give me my graph, right? And I don't have a lovely image of my graph, but actually, yes, I do, right? You can see there's my lovely image of my graph where I've plotted 1 over the temperature in Kelvin, and I've got the log of K. So here's my log of K. Here's my 1 over temperature. So if I want to determine what the activation energy, right, my slope of that line, right, is going to be the change in Y over the change in X, right? So my change in Y, right, if I pick 2 points, right, and we'll pick this point here, and we'll pick this point here as my 2 points, okay? Very well separated points, and then using the coordinates. So my change in Y, right, is going to be minus 6.6 minus a negative 10.4, right? So that's my delta Y, Y1 minus Y2, over my delta X, X1 minus X2. So my delta X is going to be 0.00195 minus my X2, which is 0.00215. All right, so I get negative 6.6 minus 10.4 divided by 0.00195 minus 0.00215. And so that gives me a slope that's equal to minus 1.9 times 10 to the fourth. That is the slope of that line, right? So now I know that that's equal to minus EA over R, right? So I want to solve for EA. So I have my slope, right? And I want to look at, to say my slope, my slope, again, equals my activation energy divided by R. My activation energy equals negative slope times R. So my slope was negative 1.9 times 10 to the fourth, had units of Kelvin, and my K is 8.314 joules per mole per Kelvin, right? And that gives me a really big number. So I'm going to convert that and say that there's 1 kilojoules per 1,000 joules, right? So my units of Kelvin cancel, my joules cancel, and I end up with kilojoules per mole, or 1.6 times 10 to the second kilojoules per mole, 160 kilojoules. So that's the activation energy for that reaction, right? So we graphically plotted our data, got the slope of the line, and from that we're able to calculate the activation energy. All right, that's the end of part 2 of sample questions. I'll be back in a few minutes for part 3.